Hi everyone. So today I'm going to be teaching you how to make my own version of a procedural art generation program in Python using sobel edge detection. So hopefully it should take an image like this, and it should output an image like this. Boom, instant art. So let's get into it. Right, great. Hi. So let's get started. First thing, we've got a fresh idle script open, and we're going to go ahead and import the Python image library, or specifically we're going to import the image class from it, and that's going to let us open up the image. And in this directory I've got a image called panda.jpg, and that's the one I'm going to be working with. Just downloaded it from Google Images, from the BBC, so hopefully that wasn't copyrighted. Probably educational, so fair use, don't sue me. Let's write a method called, let's call it draw, and it will take as its parameter the path to an image, and what it'll do is it'll load that into a variable called im. And then what we're going to do with im is, in fact, actually, since what we have is quite a small image, and if we were going to do this with much larger images, you'd probably want some downsampling capability just to make it run a little bit faster. So I'm going to make it take another parameter called downsampling, or ds, which by default is 1, so no downsampling. In theory, if the downsampling was 5, you would take every 5th pixel, or you'd resize the width and the height to a 5th of the size. So by default it's going to be 1, so there's going to be no downsampling by default. So I'm going to go ahead and find the width and the height of the image by using image.size, which is a built-in property of the image class, and we can resize it now. Say im equals im.resize, and what we want is a new height according to the downsampling and a new width according to the downsampling, and we can say that new width is equal to, or in fact, we don't even need a new variable, we can just use the same variable name and set that equal to width divided by ds, and I'm using a double slash because that means integer division, which means it'll round it down to an integer, which is important because when we're resizing it, we need the new dimensions to be integral. So we'll have the height as well, the height divided by the downsampling. And we can, when we resize the image, we give it this tuple, which is the new dimensions, and we're going to use image.antialias just to make sure that the resizing is smooth. Now what we're going to do is we need to get the grayscale image of the data. So we're going to totally discard the color data, we just want it to be in grayscale. So we can call that gray, and that's im.convert, and now we need to give it a color mode, and the mode for grayscale, for whatever reason, is L. I think it stands for lightness or luminosity, but I'm not entirely sure, don't quote me on that. So now what we've got is, if we print this out, we can see what we've got, and if we call this method with a reference to the panda.jpg file, what we've got is an image object, a PIL image object. So what we need is to get that image object and turn it into some pixel data. And the way we do that is we use the getData function. So if we run the getData function, what we'll see what that gives us is an imaging core object, and that's not very helpful, but luckily we can convert that directly to a list. And idle probably isn't going to print this out because new versions of idle, they squeeze the text. There it is, squeeze the text. So if we were to display this, it would slow down idle quite a lot. So instead what I'm going to do is I'm going to copy and paste it into Notepad, and you see that now what we've got is just what we need, which is a list of pixel values between 0 being black and 255 being white. But this isn't the most helpful thing. Actually, what we want to do is, first of all, we need to shape this. So at the moment this is a flat array, and we need to shape it into one which is two-dimensional, so like a matrix, with rows and columns as they would be in the actual image. So we can write a method to do this. We can call it shape, we can pass it the flat array, and also we just need to pass it the width, and it can infer the height by itself. So the result is going to be a grid, and at the moment I'm making it an empty list, and we're going to add rows to it as we create them. So we're going to iterate over the flat array with the variable I being the iterator. So we want to iterate over the length of the array, so I goes from 0 to the length of the array minus 1, because those are all the indexes of the objects in the array. And what we want also is to keep a track of the current row. So at the moment that's a blank list. And we want to add to the row the value of the array at that index. However, if this index I, is a multiple of that width, which another way of saying that is I mod width, which means the remainder after you divide by the width, is equal to 0, then we want to add the row to the results grid. We don't want to do this when I is 0 though, because the row is going to be blank. So we just want to say and I is not equal to 0. We can also say not I, because integers evaluate to booleans true when they're not 0 and false when they're 0, but I find that this is a bit more readable and understandable. And once we've done that, we will have added all of the rows except the last one, which never gets added. So let's just add that. And one other thing to remember is once we've added the row to the results list, we need to clear the row again. And now we can just go ahead and return the result, and that can shape our matrix. So if we take this list that we've got and we shape it, so we can call this image grid. We can say shape that list, and the width we can give it is the width that we've calculated. So now if we were to print out image grid, what we should see is instead of just printing out a flat array, it should print out a two-dimensional array. There we go. So let's copy this into Notepad again. And if we go all the way back to the beginning, we should be able to see here it's a two-dimensional list. So we should be able to see here, this is one row ending. So it's done what it said it's doing. And we can double check, in fact, that the dimensions are correct. Because if we print the len of the image grid, which is the number of rows, which is the same as the height, and if we print the len of the first row, that's the same as the width, and now we can print out next to it the height and the width, and we can ensure that these are the same value. There we go, so 371 by 660 both times. So that shape has worked correctly. Now what we need to do is we need to map all of the values in that grid. At the moment they're going from 0 to 255. They're a lot more useful to us if they're going from -k to k, or in this instance we're going to use -1 to 1. So we're going to write some methods that can do that. The first method that we need to write is called lerp, short for linear interpolation, and it takes two parameters a, b, and t. And what that does is that it takes this parameter t is between 0 and 1, and you can think of it as a proportion. So it could be a half or a third. And what we want to return is a number that is that proportion of the way between a and b. So if t was a half, we'd want the number halfway between a and b. So to do that, all we need to do is return t times b minus a plus a. And we can verify that if t was 0, then we've got this term becoming 0 and we're just returning a. And if t was 1, then we've got this term being b minus a, and when we add a, that's just returning b. And this is linear in t, so it's just going to give us the thing that's t of the way between a and b. We also want another function which does the inverse of that. We're going to call it inverse lerp. And that gives us a number that is in the range A to B, and we want to sort of reverse that process and find the proportion of the way between A and B that it is. And we can do that by, first of all, subtracting A. So we want t minus A, and that, instead of being in the range from A to B, it's now in the range 0 to B minus A. And then to get in the range 0 to 1, we just need to divide by B minus A. And I'm using the float command here to turn B minus A into a float, just in case B and A are integers, and B minus A is considered an integer. Python often does a weird thing where if you divide an integer by an integer, it will round to an integer. It's essentially like using the double slash thing, and I'm not entirely sure if this is necessary. It's just become a force of habit for me because I don't know when Python does this, and it's become a problem for me in the past. So now what we need to do is write our function which maps our image from the range 0 to 255 to the range -1 to 1. Or we're going to make it more arbitrary than that. I'm going to call it map image, or let's call it map grid, because it's not necessarily an image we're working with anymore. So it's going to take something that's in the range A to B, it's going to map it to the range U to V, and then we pass it the grid to map. So again, we're going to have a blank result. A result is going to be a grid of exactly the same dimensions, and we're going to add rows to it as and when we create them. So we're going to say for row in range len grid. So we're iterating over all of the rows, and now for each of those rows, we're going to create a row for the results table. Now we can iterate over every column in the current row, and this value here, this len grid row, shouldn't change with what row is, as we're assuming that the grid is going to be rectangular because we created it with this method. But just to be safe and for convention, I'm going to use that. And what we want now is to add to the results row. We want to lerp because we want to get it into a range, but first we want to get it out of the range. So at the moment it's in the range A to B, and what we're currently using is the value in the grid at the given row at the given column, right? So what this has done is it's taken it from the range A to B, which is going to be 0 to 255, and has inverse lerped it back to the range 0 to 1. Now what we need to do is use lerp to put that in the range U to V. And there is this is our T, our 0 to 1. And there we go. Now we add that to the results row. And once we've filled up the results row, we can add that to the result row. And once we've built up the result, we can just go ahead and return it. And you might be asking why we didn't just set the values in the grid directly, rather than creating this new grid. But Python often uses references to objects, so we would have been changing the actual grid itself rather than creating a new one. And if we wanted to map the grid to a different range while also keeping a reference to the input object which was in its original range, then we wouldn't want to touch that necessarily. I'm not sure that's necessarily going to be relevant for this, but it's always good practice just to keep in mind which objects you're messing around with. So now what we can do is map the grid from 0 to 255 to the range -1 to 1. And I'm going to rename this to data grid because we're no longer really talking about image data. And we're going to call map grid. And the original range, A and B, was 0 to 255. Our new range, U and V, is going to be -1 and 1. And we're going to pass it the image grid as the grid to map. And we could print out the data grid and just show that now this was in the range -1 to 1, but that doesn't really matter. What we need to do now is do a thing called kernel convolutions. So the way we're going to be making this art is we need to detect where the edges are in the image. And we're going to be using a technique called sobel edge detection, which uses a thing called kernel convolutions. And essentially what kernel convolutions are is you have a filter and you have a grid of pixels. And I'm going to leave some links in the description to some great resources about this, because I'm not going to do a great job at explaining it. But the idea is your filter is a smaller grid of pixels. So for example, we're going to be using this filter. I'm going to call it GX for conventions. And I need to double check that I get this right. It's going to go -1, 0, 1. That's going to be the first row. The next row is going to be -2, 0, 2. And the next row is going to be -1, 0, 1. And what happens is this filter is placed with its center. You can imagine it being placed. Obviously, it's not actually placed, but you can imagine it being placed with its center on each pixel of the image in sequence. And the number in the filter is multiplied by the number that's falling behind it in the grid. And those products are all added up. And that weighted sum is the value that's is the value that's associated with that pixel. And from that, you can create a whole new image or a whole new grid where the values of each cell are the values created by applying this filter to each of those pixels. And that's called a kernel convolution. This filter is also called a kernel. So what this particular filter, GX, is doing is it's looking for vertical edges. And we're also going to have another one called GY, which looks for horizontal edges. And you'll be thinking, why is it GX for vertical and GY for horizontal? It feels like it should be the other way around. It's GX for horizontal, GX for vertical, sorry, because they are crossed horizontally. You cross them by moving horizontally. And the equivalent for GY, they're the horizontal edges because you cross them by moving vertically. And what these numbers mean is that, and in fact, we're actually looking for the right-hand side of vertical edges. But that doesn't really matter because for reasons that we'll go into later. But what we're really looking for is a pixel where it's got a really low value on the left-hand side and a really high value on the right-hand side. And that's why you have these negative numbers to the left here and these positive numbers to the right here. So things where we're looking for a big boundary. And that's what an edge really is. It's a boundary between high intensity and low intensity. So we're looking for low intensity on the left-hand side and high intensity on the right-hand side. And if you have a pixel that's like that, pixel that's very much like a vertical edge, that's going to be given a high value in the resulting output grid. So we are going to create a method called convolve. So we're going to take a grid and we're going to apply a filter. And in fact, we also need to keep a note of what the magnitude of the input grid is. And by that I mean, like before I said that the grid could be going from -k to k, that k is the magnitude. So by default, that magnitude is going to be 1 if we don't specify what it is. So that's what our input images are. And what we're going to be returning from this method is a new grid of convolved data. So it's each cell is going to be how well the pixel in this grid corresponded or correlated to that filter that we've given it. So we're going to construct a new grid, and as always, we're going to put that in a result matrix, which we're going to populate as we create the rows. We're going to find the height of the filter, which is just the len of the filter. The number of rows is the height, and the filter width, we're going to again assume that it's rectangular, and we have to assume also that there's an odd number of rows and an odd number of columns so that we have a well-defined center to align with each of the pixels. So now we are going to find that center. So the x offset is the center in the along the x-axis, which is the filter width divided by 2, and integer division rounds it down. So at the moment, our width is going to be 3, and we want this is going to be 3 divided by 2, rounded down, which is going to be 1, which is the center because we start from 0, so 0, 1. Similarly, the y offset is going to be the filter height, and then divided by 2 again and rounded down. So now what we're going to do is go through each pixel in the initial grid. I'm still calling them pixels, even though they don't really bear any resemblance to an image anymore, because they're in a different range and they have different significance. I'm still going to call them pixels just because that's how I like to think of the grid. So we're going to go through each row, and as always for each row, we're going to be creating a corresponding row for the results. Now, we're going to be going through each column. Great. So now we've got an individual pixel in the grid, and we want to compute for that pixel a weighted sum of the values of the surrounding pixels, weighted according to the values of the filter. So we're going to be storing that in a total, a variable called total, and now we need to iterate over every cell in the filter. So we're going to be doing that with a variable called, first one called filter y, which goes through each row of the filter. And that's going to go from negative y offset to positive y offset plus 1. And the reason we do plus 1 is because the endpoint of a range isn't inclusive. So if y offset was 1, because the filter is at the filter is centered at 0, 1, then this is going to be going from negative 1, 0, 1, and 2 isn't included. So the same we're going to be doing for filter x, negative x offset to x offset plus 1. Now we need to work out the x coordinate of the position we are working with, because we've got a pixel in the cell, but now we need to work out the coordinate of which one of its neighbors we're looking at. So the x coordinate of that is the column, which is the x coordinate of the original pixel that we're working with, plus the filter x, which is going from negative to positive, iterating over the size of the filter. And y, similarly, is going to be row plus filter y. And now we need to deal with the edge cases, because obviously if you're at the top left pixel and you've got a filter over it and you're trying to look at what's to the left or above that, that's not a pixel that's actually in the image. So we need to decide what to do with the edge cases, and for different purposes you'll have different things. Sometimes you can assume that everything else outside of the image is black, and sometimes you can assume it's white. Sometimes you can assume that it's the same as its nearest neighbor. Sometimes you can assume that it is, you can tile the image. So what I'm going to do is assume that it's the same as its nearest neighbor. So if you go too far to the left, it's just the leftmost column of the image extends infinitely towards the left. So and the same for all of the other edges. So if x is less than 0, then we're going to set x back to be equal to 0. So we're dealing with the leftmost pixel. Otherwise, if x is greater than or equal to the length of the grid at this row, so it's gone off the right-hand side rather than the left, then we're going to set it equal to the length of the grid at that row minus 1, so the rightmost pixel. We're going to do the same with y. And the reason we're doing this is because we're looking for edges. So we want there to be as little change as possible, so that the boundaries of the image aren't detected as edges. If y is greater than or equal to the length of the grid, then we're going to set y equal to the length of the, not f grid, to the grid minus 1. Now we need to find the weight of this part of the filter, and we can call that filter weight. and that is going to be the filter, and the row is going to be filter y plus y offset in order to get the row of the filter. And now we're going to have filter x plus x offset, and now this will tell you the weight in the filter, so that's going to be the number, the -1, the 0, the 1, and now we need to multiply that by the actual value that's behind it in the grid, and we can get that by just getting grid yx, and we do yx first because we tell it the row and then the column, and then we need to multiply those together and add them to the total. So total increment by filter weight times grid value. And once we've computed that total, we can add it to the results row. And once we've filled up that results row, we can add it to the results. And now we've got our new convolved grid. What we need to do though is, like, as you can imagine, if the entire grid was -1, let's say, so it was its lowest possible value, and that would be if our image was completely black, then what you would get by convolving this, the values aren't necessarily going to be between -1 and 1 anymore. So we need to work out that new magnitude of the convolved grid. And we can work that out, we can call it new mag, and we can work that out by taking the sum of the absolute value of each number in the filter multiplied by the original magnitude. So we can say abs I for I in, now we can't just say for I in the filter, because the filter is a two-dimensional array. So for I in filter, I is going to be each row rather than each value. And we would need to multiply that by the magnitude. So instead, what we're going to do is we're going to create something that undoes this shape function. We're going to call it flatten. So we give that a grid, and we're going to create a new array called flat, and we're going to say for row in grid, and then for cell in row, flat.append cell. So we're going through all of them and creating a new flat array, and then we're just going to return that flat array. And we are going to iterate over the flattened version of the filter. And what we're going to return is we're going to return the result and the new magnitude. And the reason we need this new magnitude is so that we can put it back in the right range so that it can be interpreted as an image. So we're going to apply this GX filter to the data grid. So I'm going to call it xconvolved. It's going to be the new grid, and I'll call it xmag for the magnitude. And I'm going to set that equal to convolve of data grid is our grid, GX is our filter, and our magnitude is 1, which is the default, so we don't need to specify it. So I'm just going to run this to make sure we don't get any, oh no, this should be an in rather than an equals, just to make sure we don't get any errors and to make sure it's not running too slowly. There we go. And what that's done, I'm going to try and show you what that's done. We can, first of all, what this should have done is given us a new grid where the brightness of each pixel corresponds to how vertically edgy that pixel is in the image. So we can turn this back into an image by, first of all, mapping it back into the range from 0 to 255. So we're not going to keep this around forever. I'm just going to call it temp. That's going to be map grid from, at the moment it's going from -xmag to xmag. We want to bring it into the range 0 to 255, and it is xconvolved. And what we can do now is we can try and just turn this into an image quickly. So I can say image is equal to image.new, and we need to specify the size for it, and also we need to specify a mode. So as its mode, I'm going to give it L for grayscale. And the size, I'm going to give it width and height, which we've calculated. And now I can say image.putData, which is just put in all the raw pixel data, and we're going to give it flatten of temp, this data that we've collected, and then we're going to make it display. So hopefully this will show us where all the vertical edges are in the panda. There we go, this has worked perfectly. So you can see these dark parts are where it was very vertically edgy. In fact, this is where it's a vertical edge to the right. And these white parts, that's when you're getting a very big negative value. So that's where you're getting a vertical edge to the left. And as you can see, horizontal edges aren't really taken into account, and that's because this filter, GX, is symmetrical along this axis. So it doesn't really care about horizontal edges. We're going to deal with those later. And it doesn't really matter that we've gotten a difference between the left side of edges and the right side of edges, because we're just going to be using the magnitude. In fact, we're going to be squaring all of the values. So that was just to show you what's going on. We're now going to do the Y convolutions. And in fact, I'll keep that there just so I can show you the Y convolutions as well. So we'll call that GY. And that's going to be similar, except rotated. So it's going to be -1, -2, -1. That's going to be the first row. Next row is going to be 0, 0, 0. And the last row is going to be 1, 2, 1. So it's very similar, except it's switching the x-axis and the y-axis. So we're going to be calculating Y convolved and Y magnitude. Convolve data grid GY. And this is going from, there we go. Okay, so this shows the same thing, but for the horizontal edges. There. So you can see it's slightly different. Now it's showing us the horizontal edges rather than the vertical. So what we're going to do with this information is we can, this is very useful for artistic purposes, because now not only do we know where all the edges are, we know where all the horizontal and vertical edges are. We can use Pythagoras to create a magnitude of the edge, so we can work out how edgy it is in general, regardless of orientation. But we know how edgy it is horizontally and how edgy it is vertically, so we can work out the angle of the edge, in theory. So what we are going to do is exactly that. So yeah, let's get started. We need, don't know what's going on. Okay, so now we need to work out the magnitude of the edgiest edge that it ever could have found, and we can do that using the Y magnitude and the X magnitude. It's the square root of the sum of the squares of those is going to be the maximum magnitude we're ever going to get. And that's by Pythagoras' theorem. If we can call that max mag, and we can say that's X mag squared plus Y mag squared to the power of a half, which is the same as a square root. And now what we need to do is create a list of all the edges. Now I'm going to do something that's quite weird, is I'm going to store the edges, instead of as numbers, I'm going to create a new class object for them, called an edge. And what the edge is going to have is it's going to have an x coordinate, a y coordinate, a magnitude, and an angle, and we're going to calculate all of those. So we can say self.x is equal to x, self.y is equal to y, self.mag is equal to mag, and self.angle is equal to angle. And that's all we need the edge class for at the moment. So we're going to create a list of these edges, not a grid, which is why they need to store their x and their y coordinates so we can display them to the screen later. But also, I'm going to store them in a grid as well. And I know that this is going to sound a little weird, and it's going to seem a little weird because I'm storing the same objects in 2 different formats, and that's going to seem wasteful, but I just found that it makes it faster for the process of generating this art. So that's what we're going to do. And if you can think of any better ways of doing this without compromising speed, let me know in the comments, and I'll take a look at them. So we're going to go through every row in no particular convolution, but since they're both the same size, I'm just going to use X convolved. We're going to iterate over all of the rows and columns in that. But it doesn't matter. I could have chosen Y convolved, purely arbitrary, but they're the same size, so that's why it's arbitrary. And we're going to create a new row to put in the edge grid. Now we're going to go through the columns in range, len X convolved row. And again, these row and column numbers can apply to the X convolved and the Y convolved grid, it doesn't matter which. And we're going to, in fact, get the values for both. So the X value, which is the X edginess, the vertical edginess, is X convolved at this row, at this column. And similarly, the Y val is Y convolved at the same row, at the same column. So going through each pixel and finding those. Then we're going to find the magnitude, which is similarly to before, X val squared plus Y val squared, and we're going to go ahead and take the square root of that. And now we're going to divide that by the maximum magnitude, max mag, which we've calculated before. And now the magnitudes are all going to be in the range 0 to 1. And we're squaring them, and that's why it doesn't matter. Before we had the white pixels and the black pixels for the different sides of the edge. That's why this doesn't matter. We're squaring it. So the negative ones become positive. And we can work out the angle using arctan. So I'm going to go ahead and import math, the math module, and we can go ahead and use math.atan2, which is arctangent. And as you know from trigonometry, arctangent is the rise over run. It's the tangent is the rise over run. It's the opposite over the adjacent, or it's the height divided by the width. And usually use y over x for that, but we're going to be using the x value over the y value because the x value is for vertical edges and the y value is for horizontal. So atan2 takes 2 numbers, a y and an x, and now make sure it gets the quadrant right. It's essentially the same as doing atan of y divided by x, but it will handle all the edge cases in that. So we're going to do that, and we're going to give the x value as the y, and the y value is the x, which again is a bit confusing, but it's just because x is for vertical and y is for horizontal. And now we can create a new edge object. So we can call it edge, and we can say it's a new edge object at this column as its x coordinate, this row as its y coordinate, the magnitude we've calculated, and the angle we've calculated. And we're going to add it to the edge list, and we're also going to add it to the edge row. And then once we've filled up the edge row, we can add that to the edge grid. Now, what we need to do is we can start displaying the edges to the screen, really. First thing we'll do is we'll add a method to the edge class, which will return a color for it to use. Now, the way I'm going to do this is I'm going to use its angle as a sort of hue, its angle is a hue, an angle through the color wheel, and I'm going to use the HSL color space, hue, saturation, and lightness, or luminosity, and the saturation is going to be 1, and the lightness is going to be according to the magnitude of the angle. So I'm going to call this get color, and it's going to take itself, and I'm going to import a library called color. I could have written this myself, but I couldn't quite be bothered, and I couldn't quite work out the maths. So I imported one. I just downloaded it with pip install color with a U, the British way, which is actually annoying to me because I like to use it the American way when I'm programming, because for convention. So we're going to create an object called col, which is color dot. And funnily enough, whoever made this library, when they created the class object, they spelled it the American way, so that's always nice. In fact, before we assign this, we're going to calculate the hue, saturation, and lightness. So the hue is going to be, I'm going to make that the angle divided by pi, so that it's in the range, instead of being in the range 0 to pi, it's in the range 0 to 1, which is what this library expects it to be. So that's going to be self.angle divided by math.pi. And I'm going to make the saturation equal to 1 and the lightness equal to self.magnitude. And just to make everything a bit brighter, I'm going to take the square root of the magnitude. Because since it's going to be from 0 to 1, taking the square root of it keeps it in the range 0 to 1, but it just means that everything's a little bit brighter, which is quite nice. So I'm going to create this color object. And we can pass it the HSL parameters, H, S, and L. And now we can get the RGB components as col.rgb. However, this gives it in the range 0 to 1, and we want it in the range 0 to 255. So we're going to go ahead and say I times 255 for I in RGB, color.rgb. So we're going to go through each component of this RGB object multiplied by 255. This is going to throw some errors though, because it needs to be an integer usually when you're working with colors, so we're going to go ahead and round it to an integer. And also, this thing that we're returning is an iterable, and usually when you're working with colors, you want it to be a tuple. So I'm going to go ahead and make it a tuple, and then we can go ahead and return the RGB. Now what we need to do is create some sort of platform for displaying the image, and I'm going to use Pygame to do this, the Python game library, and this is going to require some quite complicated steps. So the first thing we're going to do is we're going to put this entire method, which draws the image and does all of this processing, I'm going to put that on a separate thread, and that's because it might take a while, and I want to have it running independently from the graphics thread, just so the graphics don't stall and crash. So I'm going to go ahead and import threading, and I'm going to turn this into a class called drawer, and I'm going to make it inherit from threading.thread, and we're going to give it a constructor, and it's going to be, instead of the draw function, it's going to be the constructor, which takes the image path and the downsampling, which by default is 1, and what it's going to do is, first of all, it's going to run the threads constructor, so threading.thread.initialize, and it's going to pass itself as that. And what it's going to do is store the image as a, it's going to store the image as it opens up. So we're going to open the image path that's been stored, so it's going to store that as an attribute of the class object itself, and we're going to again calculate the width and the height. That's going to be the image size, and I'm just going to copy and paste all of this, because this can all be done up here, except now this width and this height, I'm going to store them as attributes of the class object, and again, actually this image doesn't need to be an attribute of the class object. This image here does, the one that we've resized it to be. And we need this to be using the stored width and height. So that has stored the image, and also what I'm going to do is I'm going to make it, actually no, wait, we'll do that later. I was going to make it store a Pygame surface, but we haven't even initialized Pygame yet. So what we're going to do is indent all of this so that it is a class method, and I'm going to rename it to run, and all it takes is an attribute is itself. No longer needs to open the image. And this grey is going to be self.image.convert. And this width is going to be self.width, because now these are all stored as class attributes. Apart from that, those are the only changes I really need to make. We can, and instead of calling this thread like this, we're going to create an object, a drawer object. We can pass it panda.jpg as its target. And this is a thread. So what we're going to do is, instead of running this run method directly, we're going to run the thread start method, which will handle running the run method on its own separate thread. So now that we've got that, we're going to set up Pygame. So I'm going to say from pygame.locals import everything, and I'm going to go ahead and import Pygame, and I'm going to go ahead and import system and time as well, because those are always handy when using Pygame. And we're going to initialize Pygame. Then down here, after before even we've created this thread, we're going to create a screen object. Pygame.display.setMode, which is how I create a screen. And I can't remember exactly how big this image is. I think it was 660 by something or other. I'm going to go on the safe side and make it 1000, and I'm going to make it smaller later. I just don't want to make it too small. And I'm going to pass it 0, which means it's not resizable. This Pygame setup isn't really what's important, because this drawer class is going to be drawing to its own Pygame surface, which you can use in whatever way you want. You can save it as an image file, you can do whatever you want with it. But before we set that up, we are going to create the game loop. The aim for this is that you'll be able to see the program draw as it draws each pixel, which is why we've got it drawing on a separate thread. Rather than just creating an image and displaying it, I want to see the brush strokes in essence. So we're going to create this game loop, and we're going to look through all of the events in the last frame. So for event in pygame.event.get, and why don't we just create some space down here just to make it nice to look at. We want to check if the red X has been hit. So if event.type is quit, then we want to quit Pygame, and we want to exit the program. And I'm going to go ahead and add in another thing. If event.type is key down, I want to do the same thing if the escape key was hit. So if event.key is equal to k_escape, then do the same. And if we were doing anything more complicated when we were quitting, like saving the screen or something like that, we would have these two lines in a separate function and just make it call this function. But as of right now, we don't really need that. We're going to make it fill the screen with black every frame. Not strictly necessary, but we're going to do it anyway. And we're going to update the screen. So pygame.display.update. Now what we're going to do is make this drawer object have its own surface. So it says self.surface, its own surface object, which is a new pygame.surface, whose width is self.width and whose height is self.height. And we're going to go ahead and fill this with white, just so we can see where it is. Pygame.surface.fill, and this is the color code for white. And after we fill the screen here, we're going to do screen.blit, which is how you draw a surface to the screen, drawer.surface, and we're going to put it in the top left corner just for now. So we should see when we run this, hopefully not a crash, and we should see a Pygame window, a black Pygame window with a white rectangle in it. And obviously it's way too tall, and we'll make it shorter afterwards. Great. Okay, so let me just double check what that height was. What the width and the height were. So let's print, just so I can make the screen the right size. I mean, I don't have to make the screen the right size, but going to. Oh, and edges is not defined. That seems like it might be a problem. but it might be an old problem. 660 by 371. Ooh, that's interesting. It seems to be only when we close the program, so maybe not a huge deal. Let's take a look at where it is. Line 140. Here it is. Edges. I see I misspelled edges here, and I misspelled edge grid. Wow, that's really not good. And have I edge row.append and edge grid.append? Great. Okay, so that should have fixed that problem. It was 371 was the height. And we don't need to paint this black anymore. Okay, and now what we're going to do is let's just for testing purposes to see how the edge detection and the angle detection worked, we are going to go through each edge. So for edge in edges, we are going to say self.surface.set at. So we're going to set a pixel color. The coordinates of that are going to be edge.x and edge.y, and the color is going to be edge.getColor. And we're going to see how this works, and we should see it draw each of the pixel colors. If we give it a minute to load everything. No. Okay, edge object has no attribute angle. Oh, that's not good, but I thought we had it. I'm just going to delete this print statement. We don't need it anymore. Misspelled angle. Let's try this again. There we go. Oh, lightness must be between 0 and 1. That is probably because the magnitude that we've given is not between 0 and 1, because the square root of something between 0 and 1 should be between 0 and 1. So let's go ahead and print that out. Or as we're creating these objects, for now, let's see what happens if we print out the magnitude we have given. They should all be between 0 and 1. But apart from that, it did seem to be drawing the pixels correctly. Oh no, we're getting some 3. Oh no, wait, we're not. They're all between 0 and 1. These ones where it says 8 and let's see, can I pause this? Yeah. The ones where they don't have a 1 are times e to the negative something or other. So they should all be between 0 and 1. So what I'm going to do is we're probably just getting some rounding errors. So this here, I'm going to go ahead and clamp it in between 0 and 1. So we want to, this is how you clamp between two values. We want the biggest one between 0 and whatever this is. So if it's less than 0, set it equal to 0. And then we want the smallest one of whatever that is and 1. So if it's bigger than 1, set it equal to 1. And if we try this again, hopefully it should do a little bit better. And we can do some optimizations to make this run a little bit faster once you've got it working, and we'll definitely do that. There we go. Okay, so it seems to have found where the edges are. If we just take a look at our panda image again next to it. Great. So the problem with this is that we are drawing the images from top to bottom, sort of from left to right, and it's very boring. That's definitely one problem with it. In fact, everything seems a little bit too bright here. I might get rid of the square root. Yeah, we're just drawing a very boring top to bottom. It's not interesting at all. So what we want to do, and we know where the edges are and which angle they're facing. So what we want to do is try and find where the edges are and draw one edge at a time. The way we're going to do that is, first of all, we need to, and actually I want to draw them starting with the most prominent ones, the ones with the highest magnitude, and then get to the detail-y ones later. So we're going to need to create a method which can sort this list of edges by magnitude. And we're going to do an implementation of the quick sort algorithm. And I'm going to just write that down here. Quick sort. And it's going to take some edges. So if you don't know how quick sort works, I'm going to leave a link in the description to some resources about that. I'm going to go over the gist of how it works. So first of all, we need a termination case. So if there is fewer than or equal to one edge in that list, just pretend the edge list that's already sorted. Case 1, that's the degenerate case. Now we need to find the midpoint, which is the magnitude of the edge in the middle. So we're going to find the edge at this index, which is rounded down halfway through the list, and we're going to get the magnitude of that. Now we want a list of edges whose magnitude are less than that, a list of edges whose magnitude are equal to that, and a list of edges whose magnitude is greater than that. And we're going to iterate over each edge, so for edge and edges, like I said, if edge.mag is greater than the midpoint, we're going to go ahead and add that edge to the greater list. Otherwise, if edge.mag is equal to the midpoint, which is very unlikely, but still possible, we are going to want equal.append edge, and otherwise, and the only other case is that it's less, but we don't have to specify. If we less.append, so we add to the less list the edge. Now, what we want to return is we want to sort the greater list, and then we want to add the equal list, which is already sorted in a sense. Oh, don't need to write the word list. And then we want to add the less than list, and this is a recursive algorithm, so it's splitting the list into 3 different parts, sorting them all, reassembling them back together, and this degenerate case is what allows that recursion to end. So now let's go ahead and sort the list. So we're going to say edge is equal to quick sort edges. Edges is equal to quick sort edges. And if we see that now instead of drawing it from top to bottom, it's going to draw it from most vibrant to least vibrant. So we should see that start to happen. Oh, edge referenced before assignment. So we're returning an edge in line 97, which is up here. Okay, that should have been edges. And as you can see, this was quite slow, right? So before we actually test this out, I'm going to apply some optimization. These filters can actually be decomposed into 2 smaller filters, and you apply one after the other, and it becomes a lot quicker. So we're going to comment these out with a multi-line comment, and we're going to make 4 new filters actually called gx1. This one is just the following, so it's not a square filter anymore, it's just that, and we can make gx2, which is equal to -1, 0, 1, and applying gx is exactly the same as applying gx1 and then applying gx2 to the result. And you might notice that if you were to multiply these 2 matrices together, you would get this matrix, and this is called kernel decomposition. And as you can see, this has 9 entries in it, so we've got to have 9 comparisons per pixel, but these together only have 6, so that's going to make it a third quicker in a sense. So now we do the same for gy, which is very similar. The first one is -1, 0, 1, and the next one is g2 is -1. No, it isn't. It's 1, 2, 1. There we go. And now what we're going to do is, once we've applied gx1, we're going to apply gx2 to the result of this, where the magnitude is the xmag we got returned out of this, and we're going to do exactly the same for y convolved. So just apply the first filter, then apply the second filter with the magnitude that we've got, and we want to apply it on the result of the last convolution. So that should do exactly the same thing, just in 2/3 of the time. And now if we wait for this, we should start to see the pixels get drawn in order of lightness or edginess, I suppose. The quicksort algorithm itself is actually taking quite a lot of time. There we go. So we can see the lighter ones came in first, and then we got the darker ones. Now, what I'm concerned about is that these magnitudes are a little bit too high, but I'm not entirely sure why that is. Oh, it's because I'm squaring this instead of square rooting it. That is a huge problem. That explains why everything was too big. We can probably put this square root back in here now. Okay, that was a big problem. We should be able to see some more color in it now, because everything was a bit too bright before. Because I was squaring the magnitudes instead of taking the square root. So if we wait for this, we should again. There we go. Okay, that's much better. So we can see that the more horizontal edges are red and the more vertical edges are blue. Now what we're going to do is we are going to draw each of those edges as they connect to other edges. So we're going to get rid of this here, and we're going to call this the starting point. And we're going to add an attribute to each of the edges, which says whether or not they've been checked. And we'll see what you mean by checked in a sec once we start using it. First of all, if we've already checked this starting point, we just want to move on to the next one. So starting point.checked, continue, which means we move on to the next iteration of the loop. Now we want to create a stack. And if you don't know what a stack is, I'll put some resources in the description. Basically, a stack, you add objects to the end of it, and then you remove objects from the end of it. So it's last in, first out, essentially. So we want to then keep going through this stack while there's stuff in it. So while len stack is greater than 0, we want to pop the last thing off the stack. We call it current. Sorry, that should be -1, which means the last thing. And now we want to remove that from the stack. So stack is equal to stack up until the last one, but not including it. And the reason we're doing this whole thing is we want to start at a point and then move on to all of the ones connected to it before starting again at a new point. And that's why we've got this stack. We're going to build up this stack with all of the neighbors. So first of all, we want to check that we haven't already checked the current. So if current.checked, continue. Otherwise, we've now checked the current, or we are now checking the current, so we can set current.checked to be true. And we don't want to draw all of them, because all of the pixels. So as you can see, some of them were very, very dim, and it wasn't great. And the problem with sobel edge detection, which is what we were using, is that it sort of makes every pixel appear as a low-key edge. So we're going to have a threshold here. And that's, I'm going to make it 0.07. So it needs to be, the magnitude needs to be at least 0.07 before it is, before it's drawn. So now we are going to check if current.mag is greater than the threshold, which means we can draw it. We are going to draw it. So self.surface.set at, the coordinates are current.x and current.y. and the color is current.getColor. And what we want to do now also is we want to iterate over all of the neighbors and add them to the stack. And we don't need to make sure they haven't been checked, because this happens when we're actually iterating through the stack. So we're going to say for x in range -1 to 2. And this is actually going from -1 to 1 because 2 isn't inclusive. And we're also going from y in range -1 to 2. And we want, what we're doing is we're getting all of the pixels around the current one. So first of all, we want to make sure that x and y aren't both 0, because if they're both 0, that's the current pixel. So we want if x is not equal to 0 or y is not equal to 0. And we could have just said that if not x or not y, because again, integers evaluate to booleans, but I found that this is a lot more readable. Now we want to make sure that the x and y we're trying to check are actually within the image itself. So we want to make sure that y is between 0 and the length of the edge grid. And we want to make sure also that x is between 0 and the length of the edge grid at this row. And now what we need to do is stack.append edge grid current.y plus y and current.x plus x. And this is why we're saving it both in a list of edges so that we can sort it, and a grid of edges so that we can find neighbors. That's why we're storing it in both formats. Now, once we've done that, we can just really watch it. So, oh, that is a mistake. Why is that a syntax error? Oh, this should say if, not for. My mistake. So we're just going to go ahead and wait for this to load up. Shouldn't take more than a few seconds. And then we should start to see it draw lines of connected pixels. And it'll start with the line connected to the most vibrant pixel, and then it will go to the next line from the next most vibrant pixel that hasn't already been drawn or checked. And that's the aim. Hopefully we should be able to see the brush strokes. Now, it's taking quite a long time to render. So luckily, we built in this downsampling option, so we can actually make it work with an image half the size. And the screen's still going to be the same size, but the actual portion of it that it's going to be drawing to, the size of the surface that it's drawing to, is going to be half the size in each direction. So a quarter of the size in total. And that should, in theory, make it a lot faster when it's loading up the image. Okay, now from my experience using this algorithm, it shouldn't be taking this long, so this makes me think that there's some kind of problem. And I'm not entirely sure what it is. So I'm going to go ahead and put in some debug statements. I want to see when it's finished convolving. So say finish convolving, and I want to see when it starts sorting and when it's finished sorting. So let's just see when those activate. Okay, it's finished convolving, started sorting, finished sorting. Okay, so it should actually be drawing right now. So maybe we don't actually need the downsampling. But why is it not drawing? That is my question. Okay, how many starting points are we going through? Oh, did I set check to be true by default? That might be a problem. Nope, check is false. let's see how quickly we're going through starting points. So we'll call that I, and we'll print I, and then we'll add 1 to I. Let's see how quickly we're going through starting points. Okay, finished convolving, started sorting. Sorting should only take a few seconds. Finish sorting. Okay, so we're going through starting points pretty quickly, and that's concerning because it's not actually drawing anything. So what is happening? If we were to set the threshold to 0, maybe none of them are meeting the threshold. Or what else could be the issue? Oh, I know what the problem is. I was checking that y was within range when y is always -1, 0, or 1. Actually, what we want is current.y plus y and current.x plus x. That should do the trick. Oh, one more trick. This y should be a current.y plus y. Started sorting. Hopeful. Finished sorting. It's going to start drawing. It is not going to start drawing. That's fun. What is the problem here? It's because I made the stack empty, when in fact we want the stack to have the starting point in it when it first starts up. Oh, sorry about this. These are all the problems you run into when you're doing something live. Okay, started sorting. There we go. Now it's starting to draw them. Oh, that's really weird. It's drawing them all on the right-hand side of the window. And it's not drawing them in the right place either, I don't think. Like, those aren't even where those pixels go. So I'm wondering why... oh, that's probably because I set the threshold to 0. So all of the neighbors are valid and every pixel is one continuous edge. You know, while we're testing, why didn't I set the downsampling just so we can test a little bit quicker? Because once we get this working, this is most of the project itself. We're almost done. There we go. That is perfect. And now we can see it draw the image, and it's smaller because we made it smaller. But that is so much better. Now what we're going to do is make it so that it only uses maybe 2% of these initial checkpoints, because we don't need to go through all of them, because a lot of them are going to be below the threshold, but also a lot of them are just a few dots and not even many edges. So I'm going to go ahead and create a thing called a variable called edge proportion, which means we're only going to be doing about 2% of the edges. But that's not to do with size, so it's probably going to be the biggest 2% or the longest 2% of the edges. So we're going to, instead of iterating over all of the edges, we are going to go through the edges up until, we're going to round it down to an integer, edge proportion times the number of edges. That should do the trick. Now that should get rid of some of the noise in the background. There we go. Okay, perfect. Now, all we want to do is add a little bit of random variation. So this is the last little bit. We are going to, instead of drawing at the location of the pixel, we're going to put it off by a sine wave, right? So we're going to that sine wave is going to follow along the edges. So we need to have an angle that we're taking the sine of, and at the start that's going to be 0. And we're going to increment that by some number every time we draw. And the higher that number is, the more rough the noise is going to be. So I'm going to call that increment noise roughness, and I'm going to set it to about 0.1. And also we're going to want some amplitude of that noise, because sine is between 0 and 1, -1 and 1, my bad. So we're going to want to multiply that out by some amplitude. And I'm going to make that about 5. So what we want is, when we draw, we first want to calculate the noise. So the noise is going to be math.sine of noise x. And then we want to increment noise x by noise roughness. And actually we're going to multiply this noise by the noise amplitude. But this is just a number, right? We don't know in which direction sort of to move this, and we know the angle of the edge, and we're just going to make it perpendicular to this angle. And the way we do that is add to the x coordinate the noise times sine of the angle, so current dot angle, and we're going to add to the y the noise times the cosine math dot cos of current dot angle. And this line is getting a little bit messy, but hopefully that should be all that there needs to be there. And when this starts drawing, you should, oh no. Okay, we need to round these down to integers. Nope, it's going to get a little more complicated. Let's round it rather than floor it, just to make it a little smoother. And when this draws, hopefully you should see that the lines it's drawing are off by a sine wave, and you get that sort of wavy pattern over there. So we're going to go ahead and get rid of this downsampling just so we can see the image in all its glory. And in fact, what I'm going to do is I'm going to add a little delay. So we import time. I'm going to say time.sleep 0.0001. So there's a little bit of delay as it draws. And this is, I'm going to remind you again, this is running in the background of the graphics thread. So this could be drawing, you know, while the user is playing a game, the art could be drawing on the walls behind them as they move, or things like that. Okay, there we go. That delay is working, and you can really see the brush strokes. And you see it's off by the sine wave. I put it off by a sine wave. You could put it off by Perlin noise or by random numbers. You can make the colors do whatever you want. You can make the colors just change over time. But this is happy. This is all I wanted to do. What I'm going to do, one smaller thing that I'm going to do is actually what I was going to do is I was going to make it so that it moves the mouse to follow along where it's drawing, just so we can really see where the brush strokes are. But actually that's not going to show up on my screen recorder. So I'm just going to leave it like this. I'm going to get rid of this delay actually because it's annoying me. And I want this one to be done quickly because this video has been really long. But this is it. This is done. This is my procedural edge art generation with random noise. So I hope you've enjoyed following along with the tutorial. If you enjoy the format, let me know. If you wish I'd chopped it up into smaller segments and uploaded them each separately, let me know in the comments, and hopefully you will subscribe and watch my next tutorial. So thanks a lot for watching.